Hey, welcome back. Hopefully you were able to watch the video on the ratio test, and now we're going to be talking about that root test. Again, in order to determine convergence, or absolute convergence, or divergence of an infinite series. So again, you're going to see two slides. The first slide is going to be kind of my handwritten notes on the root test, and then the other one is going to be right out of the textbook, your theorem from there. So here we go. We have the series be a series with non-zero terms, and we have something that converges absolutely if the limit, now if you look, we have to take the nth root of it, of the absolute value of a sub n is less than 1. And it diverges if that limit is greater than 1, or if that limit is equal to infinity, which is greater than 1. And then the root test is inconclusive, just as we said it was with the ratio test when that limit is equal to 1. So let's get started and work on a couple of these problems and see. And there it is from the book, like I said. So if you see they're using that capital L, I may do the same thing today just to show you different ways that you can write your conclusions on these tests. You pick what works for you and just make sure you're clear with that and you'll be fine. Here are some facts that you need to know. And just to be kind of clear about that, if you have the limit of the nth root of a sub n, it's equal to the same thing as if we wrote it as the absolute value of a sub n to the 1 over n power. You know, the whole idea of how we write radicals. And the limit of n to the 1 over n power is equal to 1. And so you got to use those two important facts in evaluating using the root test. So how do we know to use the root test? Well, that's a good question. And you can see this first one that we're raised to the nth power. That is an indication right there that we're going to use the root test for this. So you have to kind of think about what it is that we're going to be doing. So if we have constants raised to powers that are involving n, we're most likely going to use this root test. Well, how do we use this root test? Well, we take the limit, again, as n approaches infinity of the nth. Now, am I going to have to worry about this being negative? No. So I'm not even going to worry about the absolute value of it because it's not going to be negative. All right. So what does that really, when you raise a power, a root, take the root of something raised to the same power, you know, just like the square root of 2 squared is going to equal 2, right? So this is just going to equal the limit as n approaches infinity of n over 2n plus 3. Well, evaluate that limit. And if you evaluate that limit, you should get 1/2. Well, 1/2, going back to the theorem, 1/2 is less than 1. So since it is less than 1, the series that's given converges absolutely, and therefore converges by the root test. It seems pretty easy, huh? You'll see in class you'll have some problems that are a little bit more complex than this. It's more the simplification of this once you take the nth root of something they have to worry about. Not so much the calculus as much as some of the algebra or the properties associated with it. Let's look at another example. Okay, so again, the complexity of this one is a little bit more difficult, not as easy as the other one, but we're going to, again, we see this nth root, or I'm sorry, the exponent raised to the nth power, which may give us an indication that we have to use the root test. Is it the only way? No, there's probably other ways that we could do it. Now I'm going to rewrite e to the 2n as e squared raised to the nth power. When you raise a power to a power, you multiply. So 2 times n is 2n. So that's what I'm going to do here. And we have n to the nth power there. You can see why I'm doing that. I'm going to, again, I'm stepping you step by step here so that you're very clear about what to do. So when you come into class or when you see these again, you know exactly what to do. So we have e squared over n all raised. See what I did there? Perfectly acceptable mathematical property do. And then from this, we already talked about what happens when you take the nth root of something raised to the nth power. We're left with this. And if we evaluate that limit, e squared is just a constant, n is getting very, very large. and the limit's going to be 0. So since the limit is equal to 0, which is less than 1, the series converges absolutely by the root test. Now, if you look at that, you'll go, all right, he wrote a little different than the one before. Right, sure, I wrote it out a little bit more, but the same basic idea. Here I used a notation from our book, that L, the idea of the limit. Here I actually showed the limit. Again, you get comfortable with something as long as you're able to show your conclusion, to talk about what test that you used and what the conclusion is and why you're able to draw that conclusion, you are going to be fine. So we're going to go look at one last one for the root test. And again, you can see it's a little bit more complex than the one previous. You can see that we have our exponent here is a little bit different. Might require some simplification. If you see here, we're still raised to that nth power. So let's get right to it. Let's take this limit and see what we can do in terms of simplifying it. Now, some people, what they like to do is, just like with the ratio test, they'll simplify it out here. So if you want to do that, we can do that. We can simplify this. Now watch what I'm going to do. I'm going to take the nth root of it, but I'm going to actually raise it to the 1 over n power. All right. So when we raise a power to a power, there's a couple things we can do to kind of simplify this. So the first thing I'm going to do is I'm going to break the numerator and denominator up like this. Right? Then we raise a power to a power. We multiply the powers. So this is really going to become n, because n times 1 over n is n over n. And this, we're going to actually distribute this. When we raise a power to a power, we're actually multiplying this power 1 over n by 1 plus 2n. So look what happens here. This times this is 1 over n, and this becomes plus 2. So there's our simplified version of this when I take the nth root of it. So really what I'm doing when I take the nth root of a sub n, it's really going to be taking the limit, as n approaches infinity, of n over 3 to the 1 over n plus 2. Let's evaluate that limit. I'm going to get something that is infinity over, well, this is going to go to 0, right? If you rewrite this, it's 3 to this times 3 squared, so I'm going to have 3 squared in the denominator. It doesn't matter what's in that denominator. We're going to get infinity. Infinity is greater than 1, so since L is equal to infinity, which is greater than 1, the series that we're given up there, the summation is n equals 1 to infinity, n to the n over 3 to the 1 plus 2n power, diverges. And that, in a nutshell, is the root test. Now, if you watch both videos, you saw the ratio and the root test. Both of them have very similar types of conclusions, a different way to approach them, meaning the ratio test, to remember how we had to do that, and the root test, taking the nth root of that a sub n, should be absolute value. Sorry, I just saw that. And remember, and I'm not going to show you an example of it, but if we do get a limit when we do the root test that equals 1, the test is inconclusive, similar to the ratio test, and then we're going to have to employ some other type of series test. In class on Thursday, when we have class, you're not only going to be finding things particular to root and ratio, but then you're going to be given a bunch of series that you're going to have to determine convergence or divergence with all the tests that are there. Okay, so hope you enjoyed this video. Come prepared for class, and John Stone out.